So next part in identifying the polarity, of course, this to finish the concept. So you can look at it as bonds. You can also look at it as a whole molecule. When you're dealing with simple substances, just like the diatomic substances, you're just only looking at the bonds, especially when you have diatomic substances. But when you have a bigger molecule, actually, what is prevalent is how you look at the molecule. And how you look at it is you have to look at it if it is symmetrical or not. So that's the way how to envision or vision out polarity is looking at it as a whole molecule. So you're looking at the symmetry, symmetrical. So let's go back to simple shapes like this one. You can imagine that because oxygen and oxygen are pulling all those electrons at the same time, at the same strength, same electronegativity, you can see that that pull would be equal and the electron density now, the what we're discussing where the electrons dwells, we call it electron density. All atoms has that and even compounds has that. So if the electron density is bulging or it resides to one part, we say that that is polar. But if it is symmetrical, meaning those electrons is distributed the same, just like this, the distribution would look like an egg, a perfect egg probably. You only have to look at symmetry on two sides, not necessarily on four sides. So as you can see here, you can see that the symmetry is, you have symmetry here and here from left to right, and you also have symmetry from up and down. So it's already symmetrical because all these non-polar substances would look like this, or diatomic substances would look like this. They would have a symmetry from left to right or probably from top to bottom, or usually that's the case, left to right and top to bottom. Or if you have a perfect circle, of course, if you have a perfect sphere, I mean, if you have a perfect sphere, so that is also symmetrical, just like CH4. They are polar substance, non-polar substances. Oh, going back to that topic, if you have a more complicated compound, meaning it has many bonds and many atoms, just like CH4, you can see that this type of compound is also symmetrical. Since carbon, those hydrogen are distributed all throughout in four dimensions, actually in three dimensions, I actually you already have we should already talk about three dimensions here, not just a flat discussion, but here you would be envisioning that CH4 would dwell at actually at a corner of a cube. So you can see that that is all those angle here is 109.5. So we can actually compute that 109.5 if you have a equal division um of your dimension, I mean of your three dimension into four four equal spaces. So that's 109.5. So the way usually talk this in material science, we draw a cube and we compute using trigonometry. Of course, we're not going to that, but there, take note that the angle between them is 109.5 for all the hydrogen distributed symmetrically, all those space, this three-dimensional space. So you can see that it is drawn like this in a three dimension, and for a two dimension, actually, it looks like this, but of course, a three dimension represented in two dimension is not really that um, uh, the actual. Okay, or maybe we can use yes, because I'm using a software. I can use a an app, a free app. I'll open Avogadro. This is a free app. If you have a computer, you can install this. Just look it for it in the internet, and you can find this. So if I draw a CH4, okay, it will look like that. So you can see that that is symmetrical. you can see that that is symmetrical. See, it has the same angle all throughout. Okay, we can see. So that's what I mean with a three dimension. It has the same angle. This angle here is a 109.5. So that's what we say um, of a three dimension. So if you draw it in terms of a one dimension, of course, we just draw it like this. But in a three dimension, it really looks like this. Okay? So that's what I mean. That's what I mean when I say the two dimension drawing. This doesn't really describe the molecule uh, three dimensionally. So anyway, we can see that this is um, of course, even. So I think we have an option here. Maybe I can open another app here. I think Chem Basic, Chem Sketch, Chem Basic. No, Chem Sketch, Chem Sketch. No, Chem Sketch. The other one. So why? I just want to draw it. Okay. So basically, if you draw it in a Chem Sketch, uh, and then I'll forward it to 3D viewer, of course. 3D viewer. See? So it's the same. So we have the same structure of CH4. It looks like this in a three dimension. Actually, it looks more of a like this, um, like that. It looks more like that. But of course, using only a two dimension, just like paper or board, we have to resort because we're not using a computer during discussion face to face. So just bear in mind that it looks more similarly like this. If we can just zoom in and look at the atoms and molecules. So it looks like this, but it would be helpful if we just be looking at it like this. Stick, ball and stick. We call this ball and stick model, while the other one is space filling model. So actually, it's spherical. As you can see, you have a sphere, you have a spherical, and all the electron density is distributed all throughout equally. Okay, so therefore we say that this substance CH4 is a non-polar substance. Okay, so that's what how you look at a molecule um, in terms of polarity, in terms of symmetry. So if it is symmetrical, meaning it is distributed all throughout, we say that those substances are non-polar. Another example is, of course, your the family that goes with CH4. Again, CH4 is a methane. It is the one which is mabaho or another. There are a lot of those in CR, especially those news about an explosion from a particular comfort room wherein it is natural, no bomb was put into it. So actually, the culprit of that is this one, this guy over here, the methane, because methane is just a byproduct of a your natural decomposition of your organic matter. So as you can see, it is so simple. So any organic substances will the simplest of that decomposition would yield a methane. So just like our poops. In fact, it is the main component of biogas, wherein you have um, all those garbage, solid waste, or any kind of waste which is biological or organic. and then it is turned into a fuel. So that fuel, the culprit of that is this one. Because it's really combustible and it is a non-polar substance. So the family of this is actually also non-polar. Why? For example, this is what is the substance again? It is called methane. In organic chemistry, the family of that is under the family of alkane. So when you say family of alkane, first is methane, and the next to it, which is a two carbon C2H6, is actually called a ethane, and then the next one is actually the content of LPG, which is propane and butane and propane. You can already see that these are the fuel for your lighters. Okay, actually this is also the fuel for your LPG. Butane and propane. It looks like this. As this, the other one is a C3, CH3, C3H8, and the other one is a C4H10. So they are non-polar substances. Why? Because as I mean, anyway, we can draw because I already opened apps here. I can delete one and I can really draw one, two, and then three. So this is a propane. This is a propane. Propane. If you have a propane, you can see that you can see that the molecule is has a symmetry. It looks like this. It looks like this. Okay. It somehow looks like this. It somehow bulges like that, but you can see it has a symmetry. See? Of course, I'm not good at drawing because I'm a chemical engineer, not a civil engineer. So it looks like that, but again, it has a symmetry, meaning the left and the right still the same. Although it doesn't have a symmetry up and down, but again, if you look only at symmetry, you only have to look at it at two sides. If the two sides are symmetrical, then it's already symmetrical. Okay? So this one, as you can see here, eh, that one, see, it looks like this in terms of a drawing. See, look like this, meaning the left and the right is the same. Therefore, it's a non-polar substance. Okay? So that is a non-polar substance. So even if we draw C4H10, we can add another carbon here. We can add another carbon. Okay? And it looks like that. Okay, it's still symmetrical. See, it's still symmetrical. Now it would look like this. It somehow looks like this. Okay, it somehow looks like this. um, the oblate is somewhat looks like that. Okay, so you can see an egg somewhat directed along this side, this side. Of course, that would be that would be that would be an egg which has a symmetry at the left and right. So that would look like an egg. So if it looks like an egg, again, it is symmetrical from left to right. Therefore, we can say that is a non-polar substance. Non-polar. So as you can see here, you're already talking about bigger molecules wherein you have a lot of bonds. So that's how you see polarity in two terms. In terms of bonds, electronegativity, in terms of symmetry, looking at the whole molecule. Actually, you have a computation here, but we will just uh, extract. I mean, we will not make it as a learning outcome. Computing the dipole moment. Actually, it has a dipole moment. We can compute that, but we will just eliminate some computations, of course, for you not to really be, I mean, not be so hard. So look at it as like drawing, because you can already draw now as much as possible because of the Lewis structure. That's why we first have our Lewis structures, so that you can already imagine symmetry for molecules. Okay? So thank you for this learning outcomes, for listening. to identifying polarity. So I hope you can already identify polarity. If not, look at the book, look at the LPs, so that you can practice um, looking at the polarity of substances, bonds, symmetry. Okay? Thank you guys.